All right, that's what you have on that.
Is it something like they're able to decrease the impact time and thus more force goes through?
Okay, that's not bad. Okay, so let's think of it. If you reduce the impact time, okay, so power is how fast the work is done, right? All right, so how fast the work is done, how fast the energy is transferred, how fast the energy is converted, either way. All right, so the shorter the impact time is, larger the power is going to be, right? All right, so shorter the impact time is, the larger the power is going to be. That's what it means. Okay, let's skip to the same thing. How about the impulse? Do you think in both cases, they deliver the same impulse? The guy who's breaking a single brick versus a guy who's breaking 4 bricks at a time, are they delivering the same impulse? Okay, so they have the same strength. They're not equally powerful. The guy who's breaking 4 bricks is actually more powerful than the other guy, despite the fact that they're equally strong. How about the impulse? All right, do they generate the same amount of impulse? What do you guys think? Okay, these are interesting mind twisters. Hold on, I'm just noticing that I'd be probably slightly better if I had my iPad. All right, so the guy who's breaking 4 bricks at a time is moving his hand much faster than a guy breaking 1 brick at a time. Okay, so what do you suppose the reason for it is? Okay, guys, here's the reason. All right, guy's an expert. Versus novice.
The computer displays the results. First, the novice.
Novice versus expert. What's the difference? Impact time is much shorter in the case of the expert, right? Why? Because his hand is moving much faster. Question is, why is that his hand is moving faster than a novice? Guys, you're a novice. I'm a novice. Most of us are novices. I've never broken a brick before by hitting it. All right. But I can move my hand just as fast as an expert does. There's no question about it. Okay. You can come up with the same technique. You watch the guy a couple of times, a couple of tries, you can execute it just as well. Except that guy's going to be able to break the bricks maybe 100% of the time. And if I'm lucky, I'm probably going to break one after I tried 20, 30 times. All right. What's the difference? Difference is confidence. Difference is confidence. The expert, this guy had done it 1,000 times. So he's gonna move his hand regardless, and he knows he's not gonna break his hand. All right, he's got that understanding. He had done it 1,000,000 times. If I'm a novice, I'm afraid that I'm gonna hurt myself. So I may make it look like I'm doing a good job, but in the last second, you will just. So it's the difference. All right. The more powerful guy is more powerful in the sense that he was able to transfer the energy faster. Both of them are equally strong. All right, both of them are equally strong. The guy who's more powerful is able to transfer the energy more. Okay, so the next question is, let's do a comparison. Who's going to be able to generate a larger impulse? The guy who's breaking the brick or the guy who's not breaking the brick? What do you guys think?
I think it's going to be the same.
All right, so who's generating a larger impulse? Now, you have to go back and think about the meaning of impulse. So what's impulse in this case? Impulse is change of momentum, right? Change of momentum. So change the momentum of the hand. What happens to change the momentum of the hand? Let's pretend that you're going to hit the brick at 50 miles per hour. So your hand is going to go from 50 miles per hour to 0 if it doesn't break, right? And if it breaks, okay, your hand is going to slow down, but the change of momentum is going to be smaller, right? Okay, in reality, breaking a brick is going to generate a smaller impulse, believe it or not. It's going to generate a smaller impulse. The impulse is going to be smaller if you can break it. Impact time is going to be shorter, which means that the force that you're generating is going to be larger during impulse. Okay, despite the fact that both guys are equally strong, the guy who's actually breaking the brick is generating a larger amount of force, and the other guy who's not breaking it is not hitting it with the maximum amount of force that he could. That's the difference. He's generating a much larger impulse, but his impact time is much larger. As a result, the force is not large enough to break the surface. All right, so in essence, the guy who's breaking the brick, despite the fact they're equally strong, that guy's hitting it with his maximum strength. The other guy's not hitting it, not as fast. That also means that the amount of force that he's generating is not large enough. Okay, that's an interesting way of looking at it. All right, let's try to come up with the best answer. Okay, guys, just put your answer in the chat. Put your answer in the chat. All right, so we got 6, 7, 8, 9, 10 responses. Okay, so this is the action and reaction force, right? So, which means that the forces will be identical. So you guys got that. Beautiful. All right, you guys didn't get fooled. All right, so that was good. Action and reaction force. Conservation of momentum is the concept that we're focusing on this week. All right, so it's a head-on collision between A and B. It's exactly the same as hitting a brick or a person getting hit by a train. Or head-on collision between a car and an SUV. Action and reaction forces will be the same. So action and reaction forces in both cases will be the same. All right, so let's go over the derivation one more time for this one. So head-on collision between two masses, mass 1 and mass 2. Action force is acting on mass 2, and the reaction force is acting on mass number 1. Okay, let's take a look at the impulse. Impulse to generate both masses. Impulse generated on the first mass is going to be due to the reaction force. And the reaction force is going to act on this mass for a duration of delta t. So what happens during impulse, the momentum is going to change. Its motion is going to change. Its velocity is going to change. It's going to go from an initial to a final value. Likewise, the action force is going to act on mass number 2 for this duration. And what happens is velocity of the second mass is going to change within that duration. So we're looking at the total impulse of the system. Okay, so the system is known as an isolated system. Whenever we talk about a system, we're dealing with a system of colliding or interacting masses, the objects, the particles, depending upon the situation. All right, so we're dealing with the mass of the interacting masses. We're dealing with the system of interacting masses. And we're looking at the total impulse of the system, not impulse of the individual items. We're looking at the total impulse of the system, a system containing these colliding objects. So you take the impulse of the first one. All right, it's the reaction force and its duration on the first mass. Action force and its duration on the second mass. Notice that the durations, the impact times are the same. So you factor that out. Then you have the change in velocity of the first mass plus the change in velocity of the second mass on the right-hand side of the equations. All right, so this is the statement of the net force. What is the net force? The net force usually is what causes acceleration. All right, so the net force, external net force, is what causes acceleration. You got the net force here for acting on a duration on these two masses. What's going to happen is one mass is going to undergo a velocity change, that's acceleration. The second mass is going to undergo a velocity change, so that's also acceleration. Except the net force is going to be generated by the action and reaction forces. And action and reaction forces will have equal magnitude, and they will be in opposite directions. So which means that this net force acting on the system is going to be 0. Okay, guys. Net force acting on an isolated system is going to be 0 because you're interested in the net force acting on the system. The system is composed of colliding particles. Any force between the colliding particles become internal forces. Internal forces do not cause acceleration. All right, if you wanted to get up from the chair that you're sitting on, you have to apply a force on the ground. The ground is going to apply the same force back on you. As a result, you're able to get up. So the reaction force from the ground becomes the external force acting on your body that allows you to be able to get up. You cannot grab the other arm and then try to pull yourself up. Internal forces would not allow you to accelerate. Okay, so net external force acting on an isolated system becomes 0. All right, so that's what it means. Which means that the impulse is going to be 0, which means that change in momentum is going to be 0. Okay, so change in momentum of an isolated system always going to be 0. All right, so distribute mass into the parentheses. So this is the change in velocity of the first mass. This is the change in velocity of the second mass. And gather the final velocity term from the left-hand side and the initial velocity terms on the right-hand side. Okay, so this represents the total momentum of the system before the impact or collision. This represents the total momentum of the system after the impact or the collision. I want you to realize that the total momentum after is going to equal to the total momentum before. All right, so we're always dealing with the total momentum of systems from now. And this is a really powerful method of solving problems. So the final momentum here is going to be this. Initial momentum is going to be that. So the initial momentum is on the right-hand side. The final momentum is going to be on the left-hand side. So total momentum of a system before and after, they will be the same. So this is known as constancy or the conservation of momentum. All right, so that's a mathematical way of looking at it. That was a derivation, so you could see where the concepts are coming from. What you need is the interpretation of it. All right, so the interpretation of this concept. Okay, so I did the derivation, I think. Okay, yeah, we did the derivation. Okay, that is the derivation. All right, so conservation of momentum from a math perspective. In the absence of an external force acting on an isolated system, only forces are internal forces, or action and reaction forces. Action and reaction forces will become the internal forces of a system. Internal forces will not cause the system to accelerate. That's what it means. So, which means that the total momentum before impact and the total momentum after the impact will be equal to each other. So that's the model that we're pursuing. Okay, so the next thing I want to do is just want to make sure that you have a good understanding of what's going on. So let's express things conceptually. So the question is, what happens to the object's momentum if there's a net external force acting on it? Okay, so let me just emphasize the term on the object's momentum. We're not talking about a system, you're talking about a single object. Okay, so what happens to this motion if there's a net external force acting on it? Guys, if there's a net external force acting on the mass, which means that there's going to be impulse, it's going to change the momentum of that object. All right, in fact, if you isolate the force in this equation, you end up getting force causing change in momentum within this duration. Momentum is obviously the mass on at a given velocity. So what's happening because of the force, the velocity is changing. Change in velocity in time is going to be acceleration. So net external force causes the object to accelerate, which means that the net external force causes the velocity of the object to change. And what that means is the net external force is going to cause the momentum of that object to change. Okay. So far, we've been expressing the force in terms of acceleration. All right, and from time to time, we're going to start expressing in terms of change in momentum. All right, it's a much more powerful expression than mass accelerating mass. So much more powerful than, in fact, equation E equals mc squared came out of expressing force in terms of change in momentum. So that's just a very powerful mathematical method. All right, so if there's an external force acting on a mass, what's going to happen? It's going to accelerate, which means its velocity is going to change, which means its momentum is changing. Its velocity is changing, its momentum is changing. The next question is, what happens to the momentum of an object in the absence of a net external force? So what happens to the momentum in the absence of a net external force? Guys, if there's no force acting on it, what happens? There's no change in momentum. All right? There's no acceleration. If something is moving to begin with, it's going to keep on moving in a straight constant speed. So velocity is not going to change. If something at rest, it's going to remain at rest. So which means that now you fall back to Newton's first law. So that's known as inertia. So nothing is going to happen. It's just going to remain constant. Isolated system is a system that only concerns itself with colliding objects. Two masses colliding, that's your isolated system. Head-on collision between a car and an SUV, that's your isolated system. Car and an SUV. Person getting hit by a train, that's your isolated system. All right, so isolated system is a system that only concerns itself with the colliding objects or interacting objects. So what's the net external force between two colliding objects in an isolated system? Between two colliding objects in an isolated system, you only have action and reaction forces. Okay, so action force is going to act on small mass, the reaction force is going to act on big mass. And notice that action and reaction forces of an isolated system will become internal forces. They're going to be equal to each other in opposite directions. So this force summation is just going to add up to 0. So the net force of an isolated system is going to be 0. Right, so it becomes an internal force. So net force becomes an internal force, and it's 0. So which means that the isolated system itself is not going to accelerate. So the next question is, what happens to total momentum between two colliding objects in an isolated system? It's not going to be a change in momentum. Total momentum is not going to change. Total momentum before and after will be equal to each other. That's what it means. Change in momentum of one object is going to equal to the change in momentum of the other object. That's the meaning of it. All right, so the momentum for each mass is going to change the same amount. So what's the meaning of conservation momentum? Conservation momentum simply means the momentum is going to remain constant. And the final momentum will be the same. So the next question is, what conserves momentum? Absence of an external force on an isolated system. What conserves momentum is an absence of an external force on an isolated system. So the net force acting on an isolated system is going to be 0. All right, so let's go back. What is supposed to be a lecture review? Lastly, what's elastic collision? What's inelastic collision?